Hi, and welcome to a short introduction to RSA. First, let us determine two very different types of cryptographic systems: symmetric and asymmetric. Symmetric key algorithms use the same keys for both the encryption of the plaintext and the decryption of the ciphertext. The key is a shared secret between the sender and the receiver of the message. The fact that both parties must have access to the same secret key is the main disadvantage of symmetric key encryption. Asymmetric cryptography is also called public key cryptography. For the encryption, a public key is used, and for the decryption, a private key is necessary. The idea was first mentioned by Whitfield Diffie and Martin Hellman in 1976. Public key systems are based on the existence of one-way functions, also called trapdoor functions. These functions are easy to compute in one direction, but the computation of the inverse is not feasible to compute in limited time. While Diffie and Hellman presented the idea of using one-way functions, they did not actually realize one. Symmetric encryption is usually faster, since the key sizes are smaller, but it also requires a way to privately share the secret key between the sender and the receiver. Therefore, symmetric and asymmetric algorithms are often used in combination. Asymmetric encryption is used to exchange a private symmetric key, which can then be used in all subsequent communication. RSA is one of the oldest existing asymmetric cryptosystems, which can be used for encryption or digital signatures. Following the theories regarding public key cryptography by Diffie and Hellman, the trio consisting of Ronald Rivest, Rivest-Shamir, and Adleman succeeded in finding an actual one-way function. They published a detailed description of the first ever asymmetric encryption method in 1977. The patent was granted to MIT in 1983. Since RSA is relatively slow, it is often not used to directly encrypt user data. Rather, it is used to transmit shared keys. With today's state of knowledge, the prime factorization of very large numbers is very time-consuming, whereas a multiplication of prime numbers is fast and easy to compute. Therefore, it is a suitable one-way function to use for the public key system. We will call the message we want to encrypt M. Let's define E and N as our public key, and D, N as our private key. E, D, and N have to be very large positive integers, where the message has to be positive and smaller than n. In RSA, the main observation is that it is easy to compute integers e, d, and n, such that the message m to the power of e to the power of d is congruent to the message m modulo n. But even with the knowledge of the public key e, n, and even with the message itself, it is quite hard to find the private key d. For the key generation, we first take two distinct random prime numbers, called p and q. N is then computed by multiplying these two prime numbers. The third step is the computation of Euler's totient function phi, which is p-1 multiplied with q-1. This result phi of n is kept secret. We then try to find an integer larger than 1, which is smaller than phi of n, and also co-prime to phi of n. This integer is called e, and together with n it forms the public key. The last step is finding the private key d, by finding a positive integer that is congruent to 1 modulo phi of n when multiplying with e. Let's look at an example. For distinct prime numbers, we'll take 3 and 11. Now, n is the multiplication of these two factors. 3 times 11 equals 33. In the next step, we compute the Euler totient function by taking 3 minus 1 times 11 minus 1, which is 2 times 10 and equals 20. We then find an integer that is larger than 1, smaller than 20, and co-prime to 20. 7 is the smallest possible number for which this relation holds. The last step is finding the private key d. For this, we have to find a positive integer that equals 1 modulo 20 when multiplied with 7. For the value d equals 3, this relation holds. We have thus found all the necessary keys. The public key is 7 and 33, and the private key is 3 and 33. Imagine the sender wants to send a message to the receiver. For that reason, The receiver generates the keys as described in the previous step and transmits the public key to the sender. The route has to be reliable, but not necessarily secret. The public key is public, after all. The sender then encrypts his message M with the public key and sends the resulting ciphertext to the receiver. The receiver is now able to decrypt the ciphertext with the secret private key and can read the original message. For the encryption, we need the plaintext message M and the public key, consisting of the tuple EN. When we take the message to the power of E and take it modulo N, as a result, we get the ciphertext C. As an example, we want to encrypt the message M equals 4, and we will use the same key as generated earlier. We have to take the message 4 to the power of E, which is 7. This equals 16,384. This result has to be taken modulo 33 to get the ciphertext. Our concluded ciphertext C is 16. For the decryption, we need the ciphertext and the private key. We receive the plaintext when we take the ciphertext to the power of a private key D and calculate the result modulo N. With our example, the ciphertext is 16 and a private key D is 3. 16 to the power of 3 is 4096. And when we take this result modulo 33, we again get our plaintext message, which is 4. If you want to learn more about TLS, go ahead and visit our website at tlsacademy.cs.upb.de.